So if you recall from last time, we were trying to understand the mystery of why mercury concentrations in many water bodies in rural Utah are experiencing mercury contamination. And one of the hypotheses was that it was gold ore processing in Nevada that was one of the potential sources. So what I'd like to do is talk a little bit about the processes of gold ore processing that occur in Nevada and which ones might be responsible for mercury emissions. So there's three basic types of ore in Nevada, and one is the oxide, one is refractory, and one was double refractory, and each one requires a different type of processing in order to liberate the gold from the matrix. The oxide ore type has lots of sulfates, iron oxides, some carbonate, and has a lot of free mercury in it. Hg0 is elemental mercury. The refractory ore is largely made up of sulfides, iron sulfide, and the mercury is bound as mercury sulfide. And the double refractory ore has both the sulfides and large amounts of carbonate. And once again, the mercury is bound in the mercury sulfate, or mercury sulfide anyway. And the extraction techniques that are necessary for each of these differ. For the oxide type of ore, you can use cyanide heap leaching. For the refractory type ore, you can use an autoclave. And for a double refractory ore that has both sulfides and carbonates, you need to use a roaster. And it's the roaster that has the greatest potential for emission of mercury to the atmosphere. So here's an example of a cyanide heap leach technique. It starts off by piling up gold ore onto a lined pit, and then you'll pump cyanide onto the top of this heap, and it will percolate down through the ore, and it'll collect gold from that ore on the way down. And then you have your impregnated cyanide solution that comes back to a different pond, and then you pull that pregnant cyanide solution through a series of bins that extract the gold. You recycle the cyanide and you start the process over. And each one of these, basically you repeat this step over and over again for about a month or two, and at that point you have removed much of the gold from the ore itself. Now, I've had the opportunity to visit one of these cyanide heap leach pads in Nevada, and let me tell you, it has a very distinctive smell. You never forget the cyanide smell once you've seen it, and once you've smelled it. It smells very toxic. It smells almost like death. And the cyanide ponds are a beautiful blue. They look like a wonderful place to hang out if you're a bird. And of course, any bird that lands in these cyanide pods will be killed by them from their toxicity. So the mines put nets over these to prevent birds from getting into them. The autoclave technique is basically for the sulfide ore that doesn't have the carbonates in it, and you can basically put it into an autoclave and put the crushed ore in there with water and sulfuric acid, and you raise the temperature to 200 degrees C, you raise the pressure to 24 atmospheres, and you lower the pH to below 1. And all of that is necessary to break it down, and then you can take that ore and put it through a cyanide solution to extract the gold once it's been broken apart from the matrix. So from the mercury perspective, the mercury was a mercury sulfide, and in this environment it is oxygenated into mercury sulfate. Mercury sulfate happens to be water soluble, so it's easy to remove from wet scrubbing. And the wet scrubbers that they have on these autoclaves can remove 99.8% of the water soluble mercury. The roaster is the one that I was referring to that has the highest potential for atmospheric emissions of mercury, and it basically puts the crushed ore into a furnace and roasts it at 550 degrees C. That breaks down the matrix itself, and you can extract the gold using a cyanide solution from the oxide ore that's been treated in this manner. Essentially, it's dealing with the pyrite, the iron FeS2, and turning it into hematite, and it's taking the calcite and turning it into gypsum. But we don't really care about that. What we care about is what's happening to the mercury. And once again, at these high temperatures, the mercury sulfide is combining, or is basically being broken apart at these high temperatures, and it's liberating elemental mercury, and the oxygen is reacting with the sulfur to create sulfur dioxide gas. And so you have two pollutants that would come out of the stack if it were left untreated. You'd have elemental mercury and sulfur dioxide. And 80% of all the mercury that was in the ore is liberated during the roasting process. And you have to have specialized equipment if you want to try and remove the mercury and the sulfur dioxide from the stack before it goes to the atmosphere. So how much mercury is emitted by these Nevada gold mines? And the best way would be to do continuous emissions monitoring, but that's expensive and difficult to achieve. And if these emissions were accurately known, then we could feed them into regional chemical transport models to determine where that mercury is transported to and how it's removed from the atmosphere. However, the emissions are highly uncertain because the gold mining industry was not required to continuously monitor these emissions under the current law. And we also don't know the speciation of the mercury emissions. We don't know if it's coming out as elemental mercury. We don't know if it's coming out as water-soluble mercury. And as you'll see in the next few slides, it makes a huge difference on where that mercury is going to be removed, depending upon whether or not it's water-soluble or not. So why are these mercury emissions unregulated? Well, the gold mines realized that the government was about to regulate, so they intervened and said, we're going to voluntarily reduce our mercury emissions. And they did this in 2000. And they estimated that their current emissions at that point were 10.5 tons of mercury per year. And they have since self-reported that their mercury emissions have decreased each year. And supposedly by 2006, they were only emitting around 2 tons per year. And they were doing this by installing scrubbing technology on the roasters. However, because these were self-reported numbers, the public was quite skeptical. And the state of Utah was particularly skeptical because of our mercury problems. And so the state of Nevada started requiring all gold mining facilities to submit stack emission test results in 2007, and annual tests are mandated thereafter. So the 2007 emissions testing identified some serious problems with emission controls, especially at the Jarrett Canyon Roaster facility. And that Jarrett Canyon Roaster facility by itself was emitting more than 10 tons of mercury. So the self-reported values were certainly not accurate. And as a result, Nevada shut down the facility in March of 2008 and required a complete retrofit for mercury removing devices and testing thereafter. So if the mercury is coming out of these sources, where is it going to end up? And how can we track how it's changed over time? Well, the receptors that we have would be ice cores. And the ice cores that we have are mainly located in Wyoming. In the Wind River Range, there are still some glaciers. They're not super deep. They don't go back a super long period in time, but they do provide some information. We can get some information over the last couple of hundred years from lake sediment cores. And then I myself have been taking direct atmospheric mercury measurements, as have other researchers as well. So let's take a look at some of the results of the mercury in the ice core from the Upper Fremont Glacier in Wyoming. So back in pre-industrial, the mercury concentrations were less than 4 nanograms per liter. And then you'll see that there's a big spike in 1815. That was the Tambora volcanic eruption. Remember that mercury is one of the things that's emitted from volcanoes. And so we had the Tambora eruption in 1815, we had the Krakatoa in 1883, were very large, globally impacting eruptions. And then we had Mount St. Helens in 1980, which was a pretty small eruption compared to the others, but was in relatively close proximity, so it had a big impact. You see the impact of the gold rush in California starting in 1849. They used a lot of mercury to extract gold from the ore in a very non-environmentally friendly manner, and a lot of that mercury was released to the atmosphere, and some of it ended up in this glacier in Wyoming. And then, starting in after World War II, there is a significant increase in the amount of mercury in the glacier. And it went all the way up to more than 25 nanograms per liter. That's more than 5 times, actually more than 6 times what it was pre-industrial. And that could be due to a lot of causes. This doesn't tell you where the mercury is coming from. It doesn't tell you the source. It just tells you the total integrated amount. And so there's a couple of things that could be going on there. We could have, the gold mining activities in Nevada have ramped up during that time period, but the amount of worldwide coal combustion has also increased significantly during that time period. And recall that mercury is also comes from coal combustion as well. So you can't really tease that out. If we look at cores that were done in the Great Salt Lake, so we have about 100 years worth of data, and basically shows that in the distant past, 100 years ago, we had mercury concentrations of about 0.3 parts per million, and it basically didn't change much from that until just recently in the last 20 years. It has decreased down to about 0.1 parts per million. So it's actually been going down over that time period. If we look at the lake, a lake in Nevada, Pyramid Lake, which is upwind of the gold mining areas, then we basically had really low concentrations before the 49ers, the Comstock era, and all that mercury was ending up in Pyramid Lake, so you had a big peak in Pyramid Lake, and then that was over, and so the input of mercury decreased, and basically you can see that there's a pretty good correlation between the lake height in blue and the amount of mercury in the system as well, at least in the last few years. And then we have some lakes in Idaho. We have Mud Lake and we have Sandhole Lake. So this isn't calibrated for years on the y-axis, but it is in depth, and the deeper you go, the older the sediments. And for Sandhole Lake, at least, you can see that there's been this gradual increase in the concentrations of total mercury, THG. And in the other lake, Mud Lake, it has not been quite as clear of a constant increase. So it's actually quite complicated trying to use these receptor sites to identify potential sources and even to understand whether or not mercury has been increasing in these ecosystems. So I was funded by the EPA to try and get a better understanding of where this mercury is coming from. And so it was a 4-year study from 2008 to 2012 to try and answer that question. And what I did is I set up a sampling site at Salmon Falls Creek Reservoir, which is just downwind of the Nevada gold mines. So it's about 100 kilometers downwind. I asked the gold mines if I could put samplers at their stacks, and they told me no. I asked if I could put it on their property. They said no, so I did the next best thing and found somebody downwind who was willing to let me put their my equipment on their ground. And then I also set up a sampling site near Antelope Island State Park here in Utah to measure the deposition of mercury to an aquatic ecosystem, in this case, the Great Salt Lake. So let's take a look at what was going on up in Salmon Falls Creek up in Idaho. So in order to do this, you have to have a mercury monitoring system. And so the system is referred to as a TEC-RAN mercury monitoring system, and it can measure three different things. It can measure the gaseous elemental mercury, the Hg0, and it can do that every 5 minutes, and it can measure the water-soluble mercury, the RGM, reactive gaseous mercury, once an hour, and it can measure particulate mercury, HGP, once per hour. The concentrations of mercury in the atmosphere are exceptionally low. Remember, we talked about ozone being in parts per billion and chlorofluorocarbons being in parts per trillion. Well, the mercury concentrations are in parts per quadrillion, so even more rare than the chlorofluorocarbons. And so you have to have very sensitive equipment, and you have to be constantly vigilant about potential contamination. And just to show you how sensitive the instruments are to contamination, I have metal fillings in my teeth, and they are a amalgam of mercury and other metals. And if I were to breathe on the inlet, the mercury coming from my fillings is enough to trigger a response in the instruments. So just to give you an idea that that's how sensitive these instruments actually are. So as I mentioned before, this instrument can measure the elemental mercury. Elemental mercury has a residence time of about 1 to 2 years in the atmosphere. It's not very reactive, and it's not water soluble. So the only way that it's typically removed from the atmosphere is through a process called dry deposition, where the gases randomly come in contact with the surface on which they stick, and then they're removed from the atmosphere. Because of this residence time and the emissions that come from coal combustion and gold production and all that sort of thing, there's actually a global background concentration of about 1.5 nanograms per cubic meter, and that's about 0.2 parts per trillion, which is about 200 parts per quadrillion. And then we have our reactive gaseous mercury. That's our water-soluble mercury, and it has a residence time of about 2 weeks, because that's the same residence time as water. The typical concentrations are a lot less, less than 0.006 parts per trillion, so that's 6 parts per quadrillion. And particulate mercury also has a residence time of about 2 weeks because it's removed by precipitation, and its concentrations are about the same as the water-soluble mercury. So here we have basically image of Nevada and Idaho. So we have the gold mines shown by the gold bricks there in central Nevada between Elko and Winnemucca. And then we have Salmon Falls Creek Reservoir, which is the red star, in just south of Twin Falls. And that's where I ended up setting up my equipment. And there was a fish consumption advisory issued for Salmon Falls Creek Reservoir in 2002. And so here's an example of some data from Salmon Falls Creek, and let's just look at the blue line, which is the elemental gaseous mercury, the one that has a lifetime of 1 to 2 years. So you'll notice that during this time period, you can clearly see the global background, the flatness of the blue line, and then superimposed upon that global background, you have an episode. We had a really large episode in early March of that year, and the concentrations went all the way up to almost 7 nanograms per cubic meter. And recall that the global background is about 1.5. And so there's a variety of things that you can do to try and understand where that's coming from. And one of the things that we can do is we can look at backward air mass trajectories. So we can look at where the air was coming from. And so if this is, say, coming from the direction of the mines, then that might be a likely source. If it's coming from somewhere else, then it could be a different source. So what were the trajectories looking like for this particular one? Well, this particular one, it took about 10 days of transport, but it did not come across from the direction of the mines, but instead went up towards Alaska and then out in the Pacific and then all the way back over to China. And this is consistent with the long-range transport of mercury from coal combustion from northern China. If you think, well, geez, how did it get transported that far? Well, it only took 10 days, and the lifetime of that mercury that's emitted in China is 1 to 2 years. So it's going to get transported around the globe multiple times in that time period. And this just happened to be a fairly strong plume that made it all the way over to where I was sampling at Salmon Falls Creek Reservoir. And so you can also use unique chemical signatures from particles that are co-transported with this type of thing to identify whether or not it happens to be associated with coal combustion or cement kilns or metal smelting. And we do have a unique signature that I was able to use to identify gold mining separate from coal combustion and incineration and biomass burning, etc. So let's take a look at the data from Salmon Falls Creek. So the concentrations in the winter time were highest, about 1.7 nanograms per cubic meter, which is only about 0.2 higher than the global background. And then it decreases to the global background in summer and fall. And then the water-soluble mercury increases during the summer, and that's consistent with the chemical reactions that are occurring in the summer to convert the gaseous elemental mercury into the water-soluble form. And if you look at the total, though, it's 99% of all the mercury that we measured at the site is this gaseous elemental mercury. That's the non-reactive, non-water-soluble mercury that has an atmospheric lifetime of 1 to 2 years. And so there's not a lot of water-soluble mercury or particulate mercury at that Salmon Falls Creek site. And just to show you an example of what the data looks like in different seasons from that area, in each one of these, winter, spring, summer, and fall, you can see that there's a significant global background, and then depending upon the season, you have peaks in the gaseous elemental mercury, and those peaks correspond to plumes of fresher mercury. Some of those are from the gold mines in Nevada, some of those are from coal combustion, some of those could be from biomass burning. So there's lots of different options for what those could be, and then it takes more detailed source apportionment to figure out the individual sources. Just give you an example, during the summer of 2006 and the summer of 2008, there were more than 10 episodes in a month during these time periods, between basically middle of June to middle of August. So that's actually quite common that you have these episodes. So you can apportion the mercury that's coming to this receptor site in terms of what fraction of it's from the background and what fraction of it actually happens during these episodes. And during this time period, 90% of all of the mercury that was being transported to the site was associated with the global background, and only 10% was associated with these episodes. So what did we learn from the Salmon Falls Creek Reservoir site? Well, we learned that 99% of all of the mercury there was the gaseous elemental mercury, the non-water soluble. Most of it's associated with the global background. So of the gaseous elemental mercury, it's predominantly composed of global background material at this receptor site. And so that means that these episodes and these local and regional sources are only responsible for about 10% of the observed gaseous elemental mercury at the site. And that doesn't bode well for the site, because even if you were to eliminate all of the regional sources of mercury, including natural ones such as Nevada, you would only have a small reduction in the total amount of gaseous elemental mercury that is observed at this site. So the global background seems to be the problem at this rural site. The question is that also true in Utah at an urban site like near the Great Salt Lake? So what I did in 2009 to 2010 is I set up a similar site on the shore of Great Salt Lake to determine the annual, seasonal, and daily variations in mercury, and determine whether or not this site was a urban, rural, or mixed site, and use the data from this to try and determine how much mercury was being deposited to the Great Salt Lake via dry deposition. So here we have the Utah 96 site location. We have the Great Salt Lake, and we're going to zoom in to this area. And we have Antelope Island in the Great Salt Lake, and there's a causeway that goes out to that. on the shore at the entrance to the causeway is where we're going to set up. So here we have the entrance to Antelope Island State Park, and there's a parking lot. And at that parking lot, there is a fenced enclosure, and that is where I set up. And that red trailer that I have is still sitting there today, although it's not currently operational for monitoring mercury. So what kind of winds do we have at the site? Well, at night, we have winds that are coming from the urbanized area, and during the afternoon, we have winds that are coming from the lake. So the site was chosen because it can simultaneously measure any type of mercury contamination that we have coming from the urbanized area, but can also look at winds coming from the west, including potential mercury coming from the gold mines of Nevada. So what kind of instrumentation did I have? Well, I had the same TechRAN mercury monitoring system. We also had a meteorological tower, and I had a rotating drum impactor to measure the chemical composition of particles as well. So we have the 8-stage rotating drum impactor in the bottom left. We have the TechRAN system mounted on a tower, and we have the red trailer attached to it where all the instrumentation is enclosed. The meteorological tower was basically 7 meters high, and it had 10 hertz measurements, so that's 10 times per second of wind and temperature, so that you can actually measure fluxes with a sonic anemometer. So what did we learn from the deployment at the Great Salt Lake? Well, the gaseous elemental mercury concentrations were 1.59. You recall that the global background is about 1.5, so it's a relatively clean site. And most of the mercury is associated with the global background, similar to what we had at Salmon Falls Creek. And there is only a little bit of the reactive gaseous mercury, gaseous oxidized mercury, that's the water-soluble mercury, and the particulate mercury. So here's an example of the gaseous elemental mercury. We have the red line, which is the global background, and so once again, you see that we're dominated by the global background, and we do have periodic increases above that as well. And if we do this on a monthly average basis, you can see that the monthly average values are very close to the global background during much of the year, but we do have some transport and local sources, kind of the January, February, March, April time period. If we look at the gaseous oxidized mercury, which is the water-soluble mercury, it tends to peak in the summer, but that's more meteorologically driven than it is sources. And then we have the particulate mercury, which also peaks during the inversion season, and that implies that there are local particulate mercury sources along the Wasatch Front that are impacting that. We also do have some peaks that occur during the summer that are often associated with wildfires. So in terms of the speciation, the mercury at the Salt Lake site is about 98% gaseous elemental mercury. So once again, it's that non-reactive, non-water soluble global background mercury is making up 98% of all the mercury at the site. So it's actually possible to apportion the amount of mercury that's being deposited to the surface due to the global background concentration of gaseous elemental mercury and local and regional sources of all of the other, gaseous elemental mercury from local sources and the reactive gaseous mercury from the water-soluble mercury and the particulate mercury. And what you can see here dry deposition in the bottom totals. Is we have the flux of mercury, the estimated downward flux from the global background is the flux of mercury, the dry deposition of mercury 8,612 nanograms global background, and the red is local and regional sources. And then if we look at local and regional sources, it's about 1/10 very significant fraction of the mercury that's being deposited is
we look at the water-soluble mercury,
the global background.
and during the winter
gaseous
months,
oxidized mercury,
the global background
is a little bit
producing
more
about
than
twice as much
the
mercury
local
down
and
to the
regional
surface
sources
through dry deposition
of
as
the
local
elemental
sources.
mercury, because it's water soluble. And then we have the particles, which are about half of that. And so the total amount that's deposited through dry deposition is essentially 10.7 micrograms per meter squared per year, but 8.6 of that is coming from the global background. And so here we have essentially a pie chart showing that 82% of the deposition, dry deposition of mercury to this Great Salt Lake is actually coming from this global background. And local and regional sources can only make up about 18% max. So EPA didn't like this answer very much, because they were hoping that it was local and regional sources that they could control and put emissions restrictions on, and thereby reduce the amount of mercury that's emitted to the atmosphere, and hopefully impact the receptor sites. But if the problem is the global background, then they need to take it up with China and the other coal-fired power plants around the world in order to make a difference in the mercury that's being deposited here in Utah. So I measured the dry deposition. Other researchers measured the wet deposition, and the wet deposition of mercury was an additional 5 micrograms per meter squared per year. And Dave Nafs at USGS measured the amount of mercury that came in through the rivers at 1.9. And so the total amount is about 17.6 micrograms per meter squared per year. So the final results from the study that I did at the Great Salt Lake is that the site was really a mixed rural and urban site, so you could get the mercury coming from both the urban and the rural sites. And it was periodically impacted by some significant local sources. However, even in this urban area, less than 50% of the measured mercury deposition was from local or regional sources. And still the majority, even in this urban impacted site, was from the global background. And like I said before, the EPA didn't like those results very much, because it wasn't something that they could then regulate. And they realized that, this is not a problem just for Utah and the rural areas of Utah, but it's a problem that's going to impact everything in the western U.S. and even the eastern U.S. because of this global background mercury concentration that will be a problem as long as we continue to have coal combustion without removing the mercury from the stacks before it's emitted to the atmosphere.